Tonight, we're going to explore one of the most profound questions humanity has ever contemplated. Not a question of science alone, though science plays a crucial role. Not merely a question of philosophy, though philosophy shapes how we think about it. Tonight, we're going to explore what would actually happen if we received contact from an intelligent civilization beyond Earth. What protocols exist? How would scientists respond? How would governments react? How would you react? By the end of this journey, you'll understand the intricate web of preparations, possibilities, and problems that surround this momentous possibility. Before we begin, if you find these deep explorations meaningful, a quick like or subscribe would genuinely help the channel grow. Now let's step into one of the most important scenarios humanity might ever face. Imagine this moment. Somewhere on Earth, at a radio telescope array scanning the heavens, an alarm sounds. Not a loud, dramatic alarm like in the movies, but a quiet notification on a computer screen. A signal has been detected, narrowband and repeating, coming from a specific point in space. The pattern is too precise, too structured to be natural. The astronomer on duty stares at the data, heart pounding, knowing that everything is about to change. The signal keeps coming, steady and deliberate, like a cosmic heartbeat reaching across the void. This astronomer faces a choice that will echo through history. What happens next? This isn't science fiction. This scenario has protocols, procedures, international agreements. Scientists have thought deeply about this moment, preparing for a day that may never come or could arrive tomorrow. The question isn't whether we should prepare, but whether we're prepared enough. The history of our search for contact. Humanity's organized search for extraterrestrial intelligence began in earnest on April 8, 1960, when astronomer Frank Drake pointed the 85-foot radio telescope at Green Bank, West Virginia, toward two nearby sun-like stars, Epsilon Eridani and Tau Ceti. For 6 hours each day over 4 months, the telescope slowly scanned frequencies near 1,120 megahertz, the emission line of neutral hydrogen. This frequency, scientists reasoned, would be universally known to any technological civilization. Hydrogen is the most abundant element in the universe. Its natural radio emission creates a logical meeting place in the electromagnetic spectrum, a cosmic landmark where civilizations might expect to find each other. Drake called his experiment Project Ozma, named after the princess in L. Frank Baum's Oz books, ruler of a land far away, difficult to reach, and populated by exotic beings. The name captured the romantic impossibility of the endeavor. Drake detected nothing artificial during those 4 months, but he had demonstrated something crucial. Searching for extraterrestrial signals was technically feasible. Radio astronomy had advanced enough that we could listen for whispers from other worlds. The previous year, in September 1959, physicists Giuseppe Cocconi and Philip Morrison had published a seminal paper in the journal Nature titled Searching for Interstellar Communications. They argued that radio telescopes had become sensitive enough to detect transmissions from civilizations orbiting other stars. Their paper sparked serious scientific discussion about methodologies for detection and the implications of success or failure. For the first time, searching for intelligent alien life moved from speculation into the realm of legitimate scientific inquiry. In November 1961, Drake organized the first SETI conference at Green Bank. Before the meeting, he formulated an equation to structure the discussion, a way to break down the enormous question of alien civilizations into manageable variables. This became the famous Drake equation, written as n char for x fp x d x for gao is phi x c xl, where n represents the number of civilizations in our galaxy with which communication might be possible. Each variable represents a factor: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually emerges, the fraction where intelligent life develops, the fraction that develops detectable technology, and the length of time such civilizations remain detectable. The Drake equation was never meant as a precise calculation. The values for most variables were, and remain, highly uncertain. Rather, it served as a framework for thinking about the problem systematically. It identified what we needed to know. Over the decades since, our knowledge of some variables has improved dramatically, while others remain completely unknown. For instance, when Drake first wrote his equation in 1961, we had no confirmed knowledge of planets beyond our solar system. Now, thanks to missions like Kepler and TESS, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. We know that planets are common, not rare. Nearly every star has at least one planet. Many have multiple planets. The fraction of stars with planets, represented by Fp in the equation, is clearly very close to 1. Similarly, the number of planets per star in the habitable zone, Ne, appears substantial. Roughly 20 to 25% of Sun-like stars have at least one rocky planet in the zone where liquid water could exist on the surface, but other variables remain deeply uncertain. The fraction of habitable planets where life actually emerges, Fl, is completely unknown. We have one data point: Earth. Life appeared on our planet relatively quickly after conditions stabilized within the first billion years. This might suggest life emerges readily when conditions allow. Or it might mean we got extraordinarily lucky. We simply don't know. The probability that life, once emerged, evolves. Intelligence is even more mysterious. On Earth, simple life existed for billions of years before complex multicellular organisms appeared, and billions more before anything resembling intelligence evolved. Intelligence might be a rare outcome, a fluke of particular evolutionary pressures that don't often arise. Recent revisions to the Drake equations have added even more nuance. In 2024, planetary scientists Robert Stern and Taras Geria proposed adding 2 new factors: the fraction of habitable planets with significant continents and oceans, and the fraction with long-lasting plate tectonics. They argue that both features are essential for complex life. Continents and oceans create diverse environments that drive evolutionary innovation. Plate tectonics regulates atmospheric carbon dioxide through the carbon silicate cycle, stabilizing climate over geological timescales. According to their calculations, the probability of a planet having both features is quite low, perhaps between 0.0034 and 0.17%. If they're correct, advanced civilizations are far rarer than earlier, more optimistic estimates suggested. Another update came from cosmologists examining the role of dark energy in star formation across cosmic history. Their model suggests that our universe has a nearly optimal amount of dark energy for generating the maximum number of stars and, by extension, the maximum opportunities for life. Universes with more dark energy would expand too quickly for structures to form. Those with less would recollapse before life could evolve. Our universe sits in a sweet spot, producing approximately 27% of its maximum possible star formation. But even in this favorable scenario, the authors suggest intelligent life might be rare. These revisions don't discourage the search. They sharpen our understanding of what we're looking for and where to look. If complex life requires very specific planetary conditions, then we should focus our searches on star systems most likely to host such planets. Sun-like stars with stable luminosity and lifetimes measured in billions of years become priority targets. Planets in circular orbits within the habitable zone, particularly those showing biosignature gases in their atmospheres, deserve intensive scrutiny. The search itself has evolved dramatically since Project Ozma's 4-month survey. The Ohio State University Big Ear Radio Telescope conducted the longest-running SETI program, scanning the skies for 22 years from 1973 to 1995. It was this program that detected the famous WOW signal on August 15, 1977, a powerful narrowband signal that lasted 72 seconds, the exact duration expected for a cosmic source moving through the telescope's field of view as Earth rotated. Astronomer Jerry Amen, reviewing the printout the next day, was so struck by the signal's characteristics that he circled it and wrote "Wow" in the margin. The signal came from the direction of Sagittarius, appeared at a frequency near the hydrogen line, and was far stronger than background noise. It bore all the hallmarks of an artificial transmission. Despite numerous follow-up observations, the WOW signal was never detected again. For decades, it remained one of SETI's greatest mysteries. Some researchers proposed it might have been a transient astrophysical phenomenon, perhaps a flare from a distant magnetar interacting with a cold hydrogen cloud. Others suggested human-made interference, though the signal's characteristics made this unlikely. Recent analysis in 2024 and 2025 by the Arecibo WOW project refined our understanding of the signal's properties. By digitizing decades of archival data using modern optical character recognition and computational analysis, researchers found that the signal was even more powerful than originally estimated, approximately 250 Janskis, rather than the 50 to 212 Janskis calculated in 1977. They also identified similar weaker signals in the data from 1977 and 1978, suggesting a possible natural explanation involving compact cold hydrogen. Clouds. The mystery isn't solved, but our tools for analyzing such signals have improved dramatically. Modern SETI has expanded far beyond single radio telescopes. The Allen Telescope Array in California, a joint project of the SETI Institute and the University of California, Berkeley, consists of 42 radio dishes working in concert. Unlike traditional radio telescopes that must choose between SETI observations and other astronomical research, the Allen Array was designed specifically for SETI, allowing it to observe continuously. Breakthrough Listen, announced in July 2015 with $100 million in funding over 10 years from investor Yuri Milner, represents the most comprehensive search to date. The project uses some of the world's largest radio telescopes, including the 100-meter Green Bank Telescope in West Virginia and the 64-meter Parkes Telescope in Australia, to survey the million nearest stars, the 100 nearest galaxies, and the galactic plane. The project also gained access to other major facilities, including the Meerkat Array in South Africa. Breakthrough Listen doesn't just search radio frequencies. It also looks for optical and near-infrared laser pulses, recognizing that an advanced civilization might use directed energy beams for interstellar communication. Lasers can transmit enormous amounts of information across vast distances. A powerful laser pulse from another star system, aimed directly at Earth, could outshine the star itself for brief moments, creating a distinctive signal our telescopes could detect. The possibility of optical SETI has opened a new front in the search, complementing traditional radio observations. The search has also gone beyond passive listening. In 1974, to celebrate the renovation of the Arecibo radio telescope in Puerto Rico, Frank Drake and Carl Sagan broadcast a message toward the globular cluster Messier 13, located 21,000 light years away. The Arecibo message consisted of 1,679 binary bits transmitted at 2,380 megahertz with a power of 450 kilowatts. The number 19679 was chosen because it's the product of two prime numbers, 73 and 23, which could be arranged as a rectangular grid to reveal a pictorial message. The image showed the numbers 1 through 10 in binary, the atomic numbers of elements essential for life, the structure of DNA, a human figure, the population of Earth, the solar system, and the Arecibo telescope itself. The message will take 21,000 years to reach M13, and any reply would take another 21,000 years to return. The transmission was more symbolic than practical, a demonstration of technical capability and a statement that humanity exists, but it sparked serious debate about the wisdom of actively announcing our presence. This controversy continues today under the banner of METI versus SETI. Should we merely listen, or should we transmit? In 1977, NASA launched Voyager 1 and Voyager 2, twin spacecraft designed to explore the outer planets. After their planetary encounters, both craft continued into interstellar space, becoming humanity's first emissaries to the stars. Attached to each spacecraft is a golden phonograph record containing sounds and images representing Earth's diversity. Greetings in 55 languages, music from cultures around the world, natural sounds like thunder and birdsong, the human heartbeat, human laughter, and 116 images showing mathematical definitions, human anatomy, landscapes, and cultural activities. The records also include printed messages from President Jimmy Carter and United Nations Secretary General Kurt Waldheim. The Voyager golden records were never expected to be found. They're more time capsule than serious attempt at communication. Voyager 1 won't reach the vicinity of another star for roughly 40,000 years, when it will pass within 1.8 light years of Gliese 445. By then, human civilization as we know it will be unrecognizably different or possibly extinct. But the gesture matters. Carl Sagan, who led the team that created the records, saw them as a message to ourselves as much as to potential aliens. We are a species capable of looking beyond our immediate concerns, imagining beings we'll never meet, and reaching out with curiosity rather than fear. The decades of searching have yielded no confirmed detection of artificial signals. This absence, while disappointing, tells us something. Either intelligent civilizations are rare, or they're not broadcasting in ways we can detect, or we haven't looked long enough or in the right places. The galaxy contains roughly 200 to 400 billion stars. We've examined perhaps a few million in any detail. The search has barely begun. To quote Jill Tarter, a pioneering SETI researcher, saying we haven't found aliens yet is like dipping a glass in the ocean and concluding there are no fish because we didn't catch any in that one glass. What contact might actually look like. When we imagine alien contact, popular culture shapes our expectations. Science fiction presents a spectrum of scenarios from benevolent visitors sharing knowledge to hostile invaders bent on conquest. The reality, if it ever occurs, will likely be stranger and more nuanced than fiction suggests. Understanding what contact might actually look like requires examining different categories of possible encounters and their implications. The most likely form of contact, by far, is detection of a radio or optical signal. This wouldn't involve aliens showing up in spacecraft. It would be electromagnetic radiation, photons that left an alien transmitter, perhaps hundreds or thousands of years ago, finally washing over Earth after an interstellar journey. The signal might be intentional, a beacon designed to announce a civilization's existence, or inadvertent leakage, radio and television broadcasts that escaped into space as a byproduct of the civilization's communications infrastructure. Intentional signals would likely have characteristics designed for detectability. They might be broadcast at the hydrogen line frequency or other prominent spectral features that any astronomical civilization would recognize. The signal would probably be modulated in some obviously artificial way, perhaps a series of prime numbers or mathematical constants like pi. These patterns wouldn't occur naturally, serving as an immediate flag that the signal carries intelligence. The signal might also include information about the transmitting civilization, their location, their nature, perhaps even an encyclopedia of their knowledge. Unintentional leakage presents different challenges. Earth has been inadvertently broadcasting into space since the development of radio technology in the early 20th century. Our earliest radio and television transmissions have spread outward in an expanding sphere, now roughly 100 light years in radius. Any civilization within that sphere with sufficiently sensitive receivers could potentially detect our presence. However, most of this leakage is quite weak. Television broadcasts, for instance, spread their signal across a wide area, rather than beaming it directionally. The signals attenuate with distance, following the inverse square law. By the time they've traveled even a few light years, they're extremely faint, buried in cosmic background noise. Military radar, particularly early warning systems from the Cold War era, produced much stronger, more focused signals. These high-powered, directional beams would be more detectable over interstellar distances than general broadcasts. Any civilization monitoring Earth might first notice us through our radar systems rather than our entertainment. The irony is rich. Humanity's first signal to the cosmos might be our surveillance and defensive technologies. If we detected an alien signal, the first challenge would be verification. Is it really artificial, or could it be a natural phenomenon we don't yet understand? This question is crucial because history shows us that many initially mysterious astronomical signals turned out to be natural. Pulsars, discovered in 1967, initially seemed so regular and precise that they were nicknamed LGM-1, standing for Little Green Men. The regular pulses of radiation, occurring with clockwork precision, seemed almost impossible to explain naturally. Only after discovering several more sources and understanding neutron star physics did astronomers realize pulsars are natural lighthouses powered by rotating neutron stars. Similarly, fast radio bursts, powerful pulses of radio emission lasting only milliseconds, were initially puzzling when first discovered in 2007. Some speculated they might be artificial, perhaps from alien spacecraft propulsion systems or directed energy weapons. Now we know they're likely natural, probably produced by magnetars or colliding neutron stars, though the exact mechanism remains under study. The verification process for a potential alien signal would be rigorous and time-consuming. First, the signal would need to be redetected, preferably from multiple locations. A signal seen by only one telescope could be local interference, equipment malfunction, or even deliberate fraud. Independent confirmation from different observatories, ideally on different continents, would be essential. The signal would need to come consistently from the same point in the sky, ruling out satellites or terrestrial sources. Its frequency and modulation would need to resist natural explanation. During this verification period, which could last weeks or months, the discoverers would have a choice: announce immediately and risk being wrong, or maintain secrecy while conducting verification and risk someone else making the same discovery and getting the credit. The tension between these imperatives has created protocols, which we'll explore in the next section, but the human element of pride, competition, and caution would inevitably play a role. Another possibility is detection of an artifact rather than a signal. This could be a probe in our solar system, either currently active or ancient and defunct. The interstellar object Oumuamua, detected in 2017 as it passed through our solar system, briefly sparked speculation about artificial origin. Its unusual elongated shape, its acceleration pattern that couldn't be fully explained by outgassing alone, and its trajectory from interstellar space made it intriguing. Harvard astronomer Avi Loeb suggested provocatively that it might be a light sail, a thin reflective sheet propelled by stellar radiation pressure. The hypothesis remains controversial and unlikely, but it illustrates how we might recognize an alien artifact, an object with properties that can't be explained by known natural processes. A more dramatic artifact scenario would be discovery of ancient alien technology on a moon or planet in our own solar system. There's no evidence for this, but it's not physically impossible. If a spacefaring civilization had visited our solar system millions or billions of years ago, they might have left probes, equipment, or structures. The surfaces of airless bodies, like the moon or various asteroids, preserve features for enormous timescales. A structure built on the moon a billion years ago would still be there, weathered only by micrometeorite impacts and solar radiation. We haven't searched comprehensively enough to rule out such artifacts. Carl Sagan and Soviet astronomer Iosif Shklovsky once speculated that Phobos, one of Mars's moons, might be artificial based on its unusual orbit. The idea was quickly disproven through better observations, but it demonstrated that even respected scientists could seriously consider the possibility of artifacts in our solar system. NASA's planetary defense programs, which catalog and track near-Earth objects, occasionally detect asteroids with unusual properties. So far, none have required an artificial explanation, but the capacity to notice anomalies exists. Direct physical contact, aliens actually arriving at Earth in spacecraft, is the scenario most common in fiction and perhaps least likely in reality. The distances are simply enormous. Even at a significant fraction of light speed, traveling between stars takes decades to centuries. The energy requirements for accelerating and decelerating a crewed spacecraft are staggering. The risks from interstellar dust and radiation are severe. While not physically impossible, interstellar travel seems vastly more difficult than interstellar communication. If a civilization capable of interstellar travel did arrive, our response options would be extremely limited. We couldn't hide, couldn't defend ourselves with current technology, and couldn't negotiate from a position of strength. We'd be entirely at their mercy. This asymmetry is one reason some scientists, including Stephen Hawking, warned against actively seeking contact. An interstellar voyage represents such an enormous investment that only a civilization with very strong motivations would undertake it. We can't know whether those motivations would be benign. The timescales involved in contact scenarios matter immensely. Radio signals travel at light speed, which seems fast, but is agonizingly slow across cosmic distances. A signal from the nearest star system, Alpha Centauri, takes 4.3 years to reach us. A reply would take another 4.3 years to get back. That's nearly a decade for a single exchange. For more distant stars, the lag grows proportionally. A signal from 100 light years away implies a 200-year round trip for communication. Civilizations separated by such distances could never have a real-time conversation. Each would send messages not to their contemporaries, but to their descendants. This time, delay has profound implications. By the time we received a signal and formulated a response, the transmitting civilization might have changed beyond recognition or gone extinct. Our response would be to a civilization that existed centuries or millennia ago, not the one that exists now. The civilization that eventually receives our response might be completely different from the one that sent the original signal. Interstellar communication isn't a dialogue, it's an exchange of time capsules. Similarly, if we detected signs of a civilization in the atmospheres of distant exoplanets, spectroscopic evidence of industrial pollutants, or other technosignatures, we'd be observing their past. A planet 100 light years away, showing signs of industrial activity now, is actually showing us what was happening there 100 years ago. That civilization could have advanced to a post-industrial phase, collapsed into extinction, or been destroyed by war or natural disaster. We'd be looking at their history, not their present. Understanding these possibilities, the vastness of space, the slowness of light, and the uncertainties involved helps calibrate our expectations. Contact, if it happens, will almost certainly be mediated by vast distances and enormous time lags. It will be ambiguous, requiring careful analysis and verification. It will challenge our patience, our assumptions, and our ability to think on timescales beyond individual human lifetimes. But despite these challenges, the search continues, driven by one of humanity's deepest questions: are we alone? Protocols and procedures, what we've already planned. Despite the enormous uncertainty about whether, when, and how contact might occur, the scientific community has developed detailed protocols for responding to a potential detection. These protocols aren't legally binding international treaties. No government has formally adopted them into law, but they represent a broad consensus among SETI researchers about best practices, a framework for handling what would be the most significant discovery in human history. The foundation of these protocols is the Declaration of Principles Concerning Activities. Following the detection of extraterrestrial intelligence, first formulated in 1989 by the International Academy of Astronautics. The document was drafted by a special SETI committee led by American diplomat and scientist Michael Michaud, with input from the International Institute of Space Law. It has since been endorsed by 6 major international space science organizations and constitutes an informal but widely respected agreement among SETI practitioners. The declaration was updated in 2010 to reflect advances in search methodologies and changes in communication technology. Then, recognizing the need for continued adaptation, the IAA-SETI Committee established a task group in 2022 to further revise the protocols. This revision process reflects the evolving landscape of SETI research, the expansion of international participation, and the increasing complexity of our global information environment. A draft of the revised protocols was presented at the International Astronautical Congress in Milan in 2024, with further refinements continuing through 2025 and beyond. The protocols outline a series of steps to be followed from initial detection through verification, announcement, and potential response. Let's walk through each stage. First, the detection itself. SETI experiments are conducted transparently. The scientists involved are free to present their work at conferences, publish their findings, and discuss their methods publicly. This transparency ensures the scientific integrity of the search and allows for peer review and replication of results. When a potential signal is detected, the discoverer's first obligation is verification. No announcement should be made prematurely. The signal must be confirmed as real, not the result of equipment malfunction, radio interference, or natural astrophysical phenomena. Verification involves several steps. The signal should be observed from multiple sites to rule out local interference. If possible, independent teams should confirm the detection. The signal's characteristics should be carefully analyzed. Its frequency, bandwidth, modulation pattern, intensity, and direction of origin. Does it come from a specific point in the sky, or does it move with a satellite? Does it appear at the same sidereal time each day as a cosmic source would, or at the same local time, suggesting a terrestrial origin? Does its frequency shift in ways consistent with the rotation of a planet or the motion of a spacecraft? During this verification process, there's no obligation to announce the candidate signal publicly. Premature disclosure would be irresponsible and potentially embarrassing if the signal turns out to be mundane. However, if media inquiries come, they should be answered honestly. The signal is a candidate, under investigation, not yet confirmed. The Rio scale, a metric developed to quantify the significance of SETI detections, should be used to communicate the signal's importance to non-specialist audiences. The scale ranges from 0 to 10, with higher numbers indicating greater significance and higher confidence. A new candidate might rank 2 or 3 initially. Only after thorough verification would it rise to higher levels. If and when verification confirms that the signal appears genuinely extraterrestrial, with all plausible natural and artificial terrestrial explanations ruled out, the protocols call for full and complete public disclosure. The discoverer must report the detection to the scientific community, the public, and the Secretary General of the United Nations. This report should include the raw data, the verification process and results, any conclusions or interpretations, and any information content detected in the signal itself. A formal report should also be made to the International Astronomical Union. The announcement should be open and transparent. No group or nation has the right to suppress or classify the discovery. Article 5 of the Treaty on Principles governing the activities of states in the exploration and use of outer space, signed in 1967, requires states to inform the UN Secretary-General, the public, and the international scientific community of any phenomena discovered that could constitute a danger to life or health, or any indication of organic life. While this treaty technically applies only to activities within our solar system, its spirit extends to any detection of extraterrestrial intelligence. That said, there are realistic concerns about governments attempting to classify such a discovery, particularly if the signal contains information that could be perceived as strategically valuable. A detailed message from an advanced civilization might include scientific knowledge, technological blueprints, or philosophical insights that some nations would want to keep secret. The protocols cannot prevent such classification, but they establish transparency as the community norm and expectation. Once the discovery is announced, the protocols call for the establishment of an international committee of scientists and experts to serve as a focal point for ongoing analysis and to advise on information release. This committee should include representatives from the International Academy of Astronautics, the International Astronomical Union, the International Telecommunication Union, the Committee on Space Research, the International Council of Scientific Unions, and other relevant international bodies. Its purpose is to coordinate the global response, ensure that all available expertise is brought to bear on analyzing the signal, and provide authoritative guidance to governments and the public. The International Telecommunication Union plays a specific role. If the signal is electromagnetic, international agreement should be sought to protect the relevant frequencies from interference. Protecting the frequency band where an alien signal is detected ensures that further observation can continue unimpeded. The ITU has procedures for this, including the ability to request that member nations minimize transmissions on those frequencies. In extreme cases, an extraordinary administrative radio conference could be convened to establish formal international protections. One of the most contentious aspects of the protocols addresses the question of response. Should humanity reply? And if so, what should we say, and who gets to decide? The original 1989 declaration included a simple statement: no response should be sent until appropriate international consultations have taken place. The procedures for such consultations would be the subject of a separate agreement. This separate agreement was drafted in 1995, but consensus on its provisions remains elusive. The core problem is, who speaks for Earth? There is no international body with the authority to compose and transmit a reply on behalf of humanity. The United Nations is the closest thing we have to a global governance structure, and the protocols suggest that consultations should take place within the UN Committee on the Peaceful Uses of Outer Space. But COPUOS deals primarily with satellite operations, space debris, and the peaceful use of space technologies. It has neither the mandate nor the expertise to craft an interstellar message. Moreover, not all SETI practitioners agree that waiting for international consensus makes sense. Some argue that if we detect a signal, we should reply immediately, acknowledging receipt and requesting clarification or more information. Delay might mean missing a window of opportunity or signaling disinterest. Others counter that a hasty response is irresponsible. we should carefully consider what we say and ensure it represents humanity's diversity, not just the opinions of a few scientists or one nation. This debate extends to the question of active SETI or MITI, messaging extraterrestrial intelligence. Should we actively broadcast our presence, or should we only listen? Some researchers have been transmitting messages into space for years, targeting nearby star systems with radio and laser signals. These transmissions announce Earth's location and humanity's existence, essentially saying, "We're here," to anyone who might be listening. Critics argue this is reckless. If there are hostile civilizations, we're painting a target on our planet. The late physicist Stephen Hawking was outspoken about this danger. He warned that an advanced civilization capable of interstellar travel might view Earth's resources as valuable and humanity as either irrelevant or an obstacle to be eliminated. We only have to look at human history, Hawking said, to see how encounters between civilizations at different technological levels typically end badly for the less advanced civilization. Colonialism, conquest, and genocide are recurring patterns in our own past. Why should we expect better from aliens? Proponents of METI counter that Hawking's fears are based on several questionable assumptions. First, any civilization capable of reaching Earth would already know we're here. For 2 billion years, Earth's atmosphere has contained oxygen, a biosignature visible to any civilization with spectroscopic technology. For the past century, we've been broadcasting radio signals into space inadvertently. If hostile aliens wanted to find us, they've had ample opportunity. Actively transmitting doesn't significantly increase our exposure. Second, a civilization advanced enough for interstellar travel would likely have access to all the resources they need without conquering inhabited planets. Asteroids, comets, and uninhabited moons contain the same raw materials as Earth, without the complications of dealing with the native population. If they wanted resources, they'd mine lifeless bodies, not invade living worlds. Third, the vast majority of science fiction scenarios depicting alien invasion assume the aliens want something we have. Our planet, our water, our resources, our biological materials. But in reality, there's nothing on Earth that can't be found more easily elsewhere. Earth's unique feature is its biosphere, life itself. A civilization interested in life would more likely study us than destroy us. These arguments haven't resolved the debate. The scientific community remains divided. Some organizations, like the SETI Institute, focus primarily on detection and analysis, leaving transmission to others. Other groups actively pursue METI, believing that establishing communication is worth the risks. The lack of international consensus means that currently anyone with access to a powerful transmitter can send messages into space without oversight or coordination. The protocols do establish one clear principle. SETI practitioners should adhere to the highest ethical standards, ensuring cooperation, honesty, and integrity in all aspects of their work. If a signal is detected, researchers should collaborate with international legal authorities and governmental entities to establish clear procedures for response. But in the absence of binding international law, these are guidelines, not requirements. They depend on the good faith and professionalism of the researchers involved. The protocols also acknowledge the importance of public communication. The discovery of extraterrestrial intelligence would generate enormous public interest, and could potentially cause social disruption. Scientists must be prepared to engage with media and the public responsibly. This means providing accurate information, acknowledging uncertainties, avoiding speculation presented as fact, and working with communications professionals who understand science and risk communication. A post-detection subcommittee within the IAA SETI committee maintains preparedness. This group includes international representation from various fields: science, ethics, law, social sciences, and communications. Their role is to provide guidance and interpretation in the event of a detection, supporting both scientific analysis and public understanding. They also continuously review and update the protocols as technology and understanding evolve. Despite decades of planning, these protocols have never been tested. We don't know how well they would function under the pressure and excitement of an actual detection. Human nature, national interests, and institutional inertia might override carefully laid plans, but the existence of these protocols demonstrates that serious people have thought seriously about this possibility. We're not completely unprepared. We have a framework, a starting point, a set of principles to guide us if that extraordinary moment arrives. The scientific response, immediate actions and analysis. When a signal is detected that appears artificial and extraterrestrial, what happens next scientifically? The process of verification and analysis is both rigorous and creative, drawing on expertise from radio astronomy, signal processing, information theory, linguistics, mathematics, and numerous other fields. Let's walk through what scientists would actually do in the hours, days, and weeks following a potential detection. The initial observation would likely come from a radio telescope conducting a survey. The telescope's data processing pipeline would flag the signal as anomalous based on preset criteria: narrow bandwidth, high intensity relative to background noise, coming from a specific direction in space rather than everywhere, potentially modulated in non-random ways. An automated alert would notify the astronomers. First response: is it real or is it interference? Radio interference is ubiquitous. Cell phones, satellites, aircraft radar, microwave ovens, even automobile spark plugs can produce signals that might trigger false alarms. The observatory's location might be chosen to minimize such interference, often in radio quiet zones protected by regulation, but perfect isolation is impossible. The astronomers would check for known sources of interference at the detected frequency. They'd examine whether the signal appears at sidereal time, which changes daily, or local time, which repeats every 24 hours. Cosmic sources appear at sidereal time. Terrestrial sources usually don't. If initial checks don't immediately identify the signal as interference, the next step is independent verification. The astronomers would contact colleagues at other observatories, asking them to point their telescopes at the same coordinates and frequency. This request would be made confidentially during the verification phase. Ideally, multiple observatories on different continents would observe simultaneously, ensuring that the signal isn't local interference affecting one site. Successful replication is crucial. If other observatories see the signal too, confidence increases dramatically. If they don't, the original detection is suspect. The famous WOW signal's greatest weakness is that it was never convincingly detected again, despite numerous attempts. Without replication, we can never be certain it wasn't a transient terrestrial interference event or an equipment glitch however unlikely that seems. Assuming the signal is replicated, analysis would deepen. The signal's frequency would be measured with extreme precision. Does it shift over time in ways consistent with a planet orbiting a star, experiencing Doppler shift due to the planet's motion? Such a shift would provide strong evidence of extraterrestrial origin and potentially tell us about the planet's orbital characteristics. The signal's bandwidth would be analyzed. Natural astrophysical sources typically produce signals spread across a range of frequencies. A very narrow bandwidth, less than a few hertz, is difficult to explain naturally and suggests artificial origin. The modulation pattern would be critical. If the signal simply consists of a carrier wave at constant intensity, it conveys no information beyond its existence. More likely, an intentional transmission would modulate the carrier wave, varying its intensity, frequency, or phase to encode information. Scientists would search for patterns in this modulation, periodicities, repetitions, mathematical sequences, anything that looks non-random. Simple mathematical sequences are a plausible starting point for an interstellar message. Prime numbers are one possibility. 1, 2, 3, 5, 7, 11, 13, and so on. These numbers aren't arbitrary human inventions. They're fundamental properties of mathematics that any technological civilization would recognize. A signal transmitting the prime numbers in sequence would be universally understood as artificial. Similarly, mathematical constants like pi, e, or the golden ratio could serve as unmistakable signatures of intelligence. If the signal contains more complex information, decoding it becomes a formidable challenge. We'd be trying to understand a message from beings whose thought processes, sensory modalities, and cultural context might be completely alien to our own. They might not perceive electromagnetic radiation the way we do. They might not think in terms of discrete symbolic language. Their mathematics might use a different base system. Every assumption we make about how to interpret the signal could potentially be wrong. However, there are some commonalities we can reasonably expect. Mathematics and physics operate the same way everywhere in the universe, as far as we can determine from observations. The laws of thermodynamics, the behavior of electromagnetic radiation, the structure of atoms and molecules, these fundamental principles appear to be universal. An advanced civilization would presumably know these laws, and they provide common ground for communication. Early in a message, the transmitting civilization might establish basic mathematical and physical concepts, building a framework we could both understand. At least this is how human SETI researchers have approached the problem when designing our own messages. For instance, they might start by defining numbers, showing how to count in their base system. Then they might demonstrate basic arithmetic, addition, subtraction, multiplication, division. Next, they could introduce physical constants, the charge of an electron, Planck's constant, the speed of light. These values are the same everywhere, providing a shared reference. Using these constants, they could define units of length, mass, time, creating a measurement system we could interpret. Visual information, if present, might be encoded as two-dimensional images. The message might include instructions on how to assemble the bits into a grid, perhaps by using prime number dimensions, like the Arecibo message. A string of bits with a length equal to the product of two primes can only be arranged as a rectangle with those specific dimensions, making the intended format clear. Within that rectangle, ones and zeros could represent dark and light pixels, creating a picture. But all of this assumes the aliens think like us, or at least anticipate how we think. They might use a completely different encoding scheme that we fail to recognize, or the signal might be encrypted, deliberately obscured to ensure only sufficiently advanced civilizations can decode it. Some theorists have suggested that highly advanced civilizations might encrypt their transmissions to filter out primitive societies. Only those with the technological and intellectual sophistication to decrypt the message would be deemed ready for contact. From this perspective, encryption is a test, a way to separate the mature from the immature. Decryption without a key is extraordinarily difficult, potentially impossible, if the encryption is strong enough. We'd be left knowing a message exists, but unable to read it, which might be more frustrating than detecting nothing at all. This scenario seems unlikely for an initial beacon, though. A civilization trying to announce its existence would probably make the message accessible, at least initially. They might broadcast a simple, unencrypted beacon that says, "We exist, here's our location, here's how to decode our detailed message," followed by more complex, potentially encrypted information. The scientific community would need to assemble teams of experts from diverse fields. Radio astronomers would handle the observational aspects. Information theorists and cryptographers would work on decoding. Linguists and cognitive scientists would consult on how to interpret symbolic communication from non-human intelligence. Mathematicians and physicists would help identify universal concepts likely to appear in the message. Astrobiologists would provide context about the possible nature of the transmitting civilization. Historians and anthropologists would offer insights into how civilizations communicate and how cultural context shapes language. The computational demands would be substantial. Analyzing large data sets, testing decoding hypotheses, running simulations, all of this requires significant computing power. Distributed computing projects, like those used in SETI Home, could harness millions of volunteer computers worldwide. The public's enthusiasm to contribute would likely be enormous. Citizen scientists could help identify patterns, test theories, and process data in ways that professional researchers, limited by funding and time, couldn't match alone. All of this work would occur under intense pressure. The world would be watching, demanding answers, speculating wildly. Conspiracy theories would proliferate. Every delay in decoding would be interpreted by some as evidence of a cover-up. Scientists would need to balance the need for careful, thorough analysis with the public's demand for immediate results. Transparency would be crucial. Regular updates, even if they amount to "we're still working on it," would help maintain public trust and counter misinformation. If the message contains a wealth of information, an encyclopedia of knowledge from an advanced civilization, the implications stagger the imagination. We might learn about sciences we haven't discovered, technologies we haven't dreamed of, philosophies that challenge our deepest assumptions. Or the message might be simpler: a greeting, a statement of existence, an invitation to respond. Either way, decoding and understanding the message would be one of the great intellectual adventures in human history. But here's a sobering thought: we might not be smart enough to understand it. If the transmitting civilization is millions of years more advanced than us, Their message might be as incomprehensible to us as quantum mechanics would be to a medieval peasant. We might recognize that information is there without being able to extract or comprehend it. This possibility is humbling but real. Intelligence has limits, and we don't know where ours lie. The global reaction, societal, political, and cultural impacts. The scientific community's response would be only one dimension of humanity's reaction to confirmed contact. The political, social, religious, and cultural impacts would ripple through every aspect of human life. Understanding how people might react requires examining psychology, sociology, history, and the structure of modern global society. Psychologists have conducted studies to gauge how people might respond to news of extraterrestrial life, though these studies necessarily have limitations. One notable study, published in January 2018 in the journal Frontiers in Psychology by researchers at Arizona State University, led by Michael Varnum, analyzed language in news coverage of past events that suggested possible extraterrestrial life. These events included the 1996 announcement of possible fossilized microbes in a Martian meteorite, the 2015 discovery of Tabby's star with its unusual dimming pattern suggesting possible megastructures, and the 2017 discovery of potentially habitable exoplanets in the TRAPPIST-1 system. The researchers used linguistic analysis software to assess the emotional tone of the coverage, looking at the frequency of positive versus negative emotion words. They found that language in the news coverage showed significantly more positive than negative emotions. People seemed intrigued and excited rather than fearful. In another part of the study, over 500 participants were asked to imagine their own reactions and humanity's reaction to the discovery of extraterrestrial microbial life. Again, responses were predominantly positive. People reported feeling more positive than negative emotions and believed the discovery would be good for humanity. The researchers concluded that, contrary to popular fears of mass panic, people would likely react with curiosity and optimism. However, it's important to note the limitations of these findings. The studies focused primarily on American respondents and asked about microbial life or distant civilizations, not aliens arriving on Earth. Cultural differences might produce very different reactions in other parts of the world, and the psychological distance between probably exists somewhere and just sent us a message is enormous. Abstract belief might not predict concrete response when faced with actual evidence. Religious reactions would be diverse. Some religious traditions would have little trouble accommodating extraterrestrial intelligence into their cosmologies. Many Buddhist, Hindu, and other Eastern traditions already include concepts of multiple worlds and diverse forms of consciousness. The discovery of alien life would confirm what these traditions have long taught. The universe is vast, varied, and teeming with beings. For the Abrahamic religions, Judaism, Christianity, and Islam, the theological questions would be more complex. Does the existence of aliens challenge the uniqueness of humanity's relationship with God? If God created aliens, did they experience their own fall, their own redemption narrative? Do they have souls? Can they be saved? These questions don't have predetermined answers. Theologians would debate intensely. Some Christian theologians have already thought about this. The Vatican's Pontifical Academy of Sciences has discussed the possibility of extraterrestrial life. In May 2008, the Vatican's chief astronomer at the time, Father Jose Gabriel Funes, stated in an interview with the Vatican newspaper L'Osservatore Romano that believing in aliens doesn't contradict faith in God. According to this perspective, God could have created intelligent beings on other worlds, just as he created humans on Earth. The Bible's silence on aliens doesn't necessarily mean they don't exist. It could simply mean the Bible is focused on humanity's relationship with God, not cataloging all of creation. However, this represents one theological viewpoint among many within Christianity. Other Christians might take a more exclusivist view, arguing that the incarnation of Jesus on earth makes humanity cosmically unique. Some might interpret alien contact as demonic deception, a test of faith. Fundamentalist interpretations might see aliens as fallen angels or as part of end times prophecy. The diversity of Christian belief means there wouldn't be a single Christian response, but many, reflecting different theological traditions and cultural contexts. Islam, with its strong emphasis on the unity and omnipotence of God, could accommodate alien life relatively easily. The Quran refers to creatures in the heavens and the earth, which some Islamic scholars interpret as potentially including extraterrestrial beings. God's creation is vast and diverse. Discovering new forms of life would simply reveal more of God's majesty. However, as with Christianity, different Islamic traditions and cultures would respond differently. Judaism, with its focus on the covenant between God and the Jewish people, might view alien contact as largely irrelevant to core religious concerns. The covenant is with humanity on earth. What happens on other worlds is God's business. Some Jewish thinkers might see aliens as part of the divine plan, while others might be skeptical or disinterested. Hinduism and Buddhism, with their concepts of countless worlds and cycles of existence, would probably find alien life unsurprising. The discovery would fit comfortably within existing cosmological frameworks that already include diverse realms of existence and beings at various levels of spiritual development. Indigenous and traditional belief systems vary enormously, but many already include concepts of non-human intelligences, spirits, ancestors, beings from other realms. For some indigenous cultures, the category of person is not limited to humans. Trees, animals, rivers, mountains can all be persons in their own right. In this framework, aliens would simply be another kind of person, different, but not categorically alien. Communication and relationship would be approached through traditional protocols of respect and reciprocity. Political reactions would depend heavily on the nature of the contact and the geopolitical context at the time. In a best-case scenario, the discovery would unite humanity, fostering cooperation as we collectively engage with this cosmic event. National borders and conflicts might seem petty in light of our shared humanity and our place in a universe containing other minds. The initial response might mirror the international cooperation seen after major disasters, when nations set aside differences to address a common challenge or opportunity. But this unity might not last. Once the initial excitement fades, national interests would reassert themselves. If the alien message contains valuable information, nations might compete for access and interpretation rights. If the message includes technological knowledge, whoever decodes it first might gain significant strategic advantages. Governments would be tempted to classify such information, keeping it secret from other nations and their own populations. The United Nations would likely play a central role, as the protocols suggest. The UN Office for Outer Space Affairs, UNUSA, might coordinate international response efforts. The Committee on the Peaceful Uses of Outer Space might be tasked with developing policy recommendations. However, the UN's authority is limited. It can't compel sovereign nations to share information or refrain from independent action. We might see a fragmented response, with different nations and coalitions pursuing their own agendas. Military and intelligence agencies would be intensely interested. They'd want to know if the signal reveals anything about the aliens' technological capabilities, particularly in areas relevant to defense. Even if the aliens are light years away and pose no immediate threat, the knowledge they possess might have military applications. Technologies for energy generation, propulsion, materials science, artificial intelligence, all of these could shift the balance of power on Earth. The temptation to weaponize alien knowledge would be strong, despite the irony of using gifts from the cosmos to fuel terrestrial conflicts. Economic impacts would be significant but difficult to predict. Financial markets might initially panic as investors try to assess what alien contact means for various sectors. Industries dependent on terrestrial assumptions might lose value, while those positioned to benefit from new knowledge might gain. But the long-term effects would depend on what information the aliens provided and how it's applied. If the message includes revolutionary scientific insights, the global economy could be transformed. If it's merely a greeting, economic impacts might be minimal. Social cohesion could be both strengthened and strained. A sense of shared humanity might bring people together, but existing social divisions could deepen if different groups interpret the contact differently. Conspiracy theories would flourish. Some would claim the aliens are allied with particular governments or groups. Others would insist the whole thing is a hoax, a false flag operation to justify global government or distract from terrestrial problems. Misinformation would spread rapidly through social media, making it difficult for accurate information to reach people. Educational systems would face new demands. Curricula would need to be updated to include information about the detection, its scientific basis, and its implications. Students would have questions that teachers must address thoughtfully. The discovery would make STEM education more appealing to some students while potentially overwhelming or confusing others. Educators would need training and resources to discuss this topic responsibly. Media coverage would be intense and, in many cases, sensationalized. Responsible journalism would struggle against the financial incentives to produce attention-grabbing headlines and speculative content. Documentaries, books, films, and television shows would proliferate, some informative, many exploitative or misleading. Celebrities, influencers, and self-proclaimed experts would offer opinions, not all of them well-informed. Sorting signal from noise would challenge the public and policymakers alike. Philosophical impacts would be profound. Humanity's place in the cosmos would be fundamentally recontextualized. We'd no longer be able to think of ourselves as potentially unique or central. The Copernican revolution, which displaced Earth from the center of the universe, would be completed. We'd be one civilization among many. Our history and struggles just one small thread in the larger cosmic story. This realization could be humbling or liberating, depending on one's perspective. Some people would find meaning and purpose in knowing we're part of a larger community of minds. Others might feel diminished, their human-centered worldviews challenged. Existential questions about consciousness, meaning, and purpose would take on new urgency. If aliens exist, what does that say about the nature of mind? Is consciousness common in the universe, or rare and precious? Do aliens have values, ethics, art, religion? Are these things universal or unique to humanity? The discovery would energize the scientific community, opening new research directions and attracting funding and talent. But it might also create tensions. Not all scientists would have access to the data. Competition for access, for recognition, for credit might become fierce. Issues of data ownership and intellectual property would arise. If one research group makes a crucial breakthrough in decoding the message, should they publish immediately or verify first? Who owns the knowledge contained in an alien message? Cultural production, art, literature, music, film, all of these would be transformed. Artists would respond to the discovery in countless ways, exploring its implications, imagining encounters, processing emotions. We'd see a flowering of creativity as humanity tries to make sense of this new reality. Some art would be celebratory, some fearful, some contemplative. All of it would contribute to our collective attempt to understand what this means for us. In the long term, assuming the aliens don't visit and no immediate threat emerges, humanity might gradually adapt to the new reality. The discovery would become part of the background of human civilization, acknowledged but not constantly dwelled upon. We'd continue our lives, dealing with terrestrial problems, pursuing personal goals, loving and losing and creating. The aliens would be out there, known but distant, a reminder of the vastness and mystery of existence, the biological and planetary security. Question one aspect of alien contact that demands serious attention is planetary protection, preventing harmful biological contamination. This concern applies most directly to scenarios involving physical artifacts or visits, but even information received via radio transmission could pose risks if we're not careful about how we apply it. The fundamental problem is that we have no idea what alien biology might be like, if it even resembles what we call biology. Life on Earth is based on carbon chemistry, uses water as a solvent, and stores genetic information in DNA and RNA. These characteristics are common because they work well under Earth's conditions. But there's no reason to assume alien life would necessarily use the same biochemistry. Based on theoretical chemistry, life could potentially be based on silicon instead of carbon, use ammonia or methane instead of water, and employ completely different molecular structures for genetics and metabolism. However, these remain theoretical possibilities rather than confirmed alternatives. If alien life uses fundamentally incompatible biochemistry, contamination risk might be minimal. Earth organisms and alien organisms might not interact meaningfully because they don't recognize each other biochemically. An alien microbe might not be able to infect Earth organisms or survive in our biosphere. Similarly, Earth microbes might not threaten alien life. This would be the best case scenario from a planetary protection standpoint. But we can't count on this. If alien biochemistry is similar enough to ours, cross-contamination could be catastrophic. An alien microorganism might find Earth organisms excellent hosts with no natural predators or immune defenses effective against it. The result could be a pandemic that makes COVID-19 look trivial. Conversely, Earth microbes might devastate alien ecosystems if we transported them there, intentionally or accidentally. This concern has driven planetary protection protocols for space missions. When we send spacecraft to Mars or other potentially life-bearing environments, we sterilize them as thoroughly as possible to avoid contaminating those worlds with Earth life. Similarly, when we return samples from other planets, we quarantine them until we're confident they pose no biological threat. The protocols are serious and extensive, governed by international agreements through the Committee on Space Research. If we detected an alien artifact in our solar system, perhaps a probe orbiting Mars or resting on the Moon, how should we approach it? The temptation to examine it closely would be enormous, but doing so might activate defensive mechanisms or release contaminants. We'd need to study the object remotely first, using cameras and sensors before any physical contact. If we decided to retrieve it, the artifact would need to be contained in a high-security biocontainment facility, similar to those used for the most dangerous Earth pathogens. Only after exhaustive study and confidence that it posed no threat would we consider exposing it to the open environment. The same logic applies to any physical message or material the aliens might send. Imagine we detected a small capsule approaching Earth, clearly artificial, slowing down as if it intended to be captured. This capsule might contain information, samples, or gifts. We'd be intensely curious, but we'd also need to be cautious. The capsule could be a Trojan horse, deliberately or accidentally carrying harmful biological or technological agents. Quarantine procedures would be essential. The capsule would be intercepted by a spacecraft and transferred to a containment facility in space, perhaps on the International Space Station or a specially constructed platform. Only after confirming it posed no threat would we bring it to Earth's surface. This might take years of study. The wait would be frustrating, but the stakes would be too high for recklessness. Even information received via radio could, in theory, pose risks. An alien message might contain instructions for building technologies that are hazardous. Imagine a blueprint for an extremely efficient energy source that, if built incorrectly or misused, could produce catastrophic explosions, or instructions for genetic engineering that could create dangerous organisms, or designs for self-replicating nanomachines that, if programmed wrongly, could turn the biosphere into gray goo. This isn't science fiction paranoia. It's a legitimate concern. Advanced technology is powerful, and power can be dangerous in the wrong hands, or if wielded without full understanding. If aliens transmitted detailed technological knowledge, we'd need to carefully assess each piece of information before attempting to build or implement it. Rushing ahead could be disastrous. Some scientists have argued that this risk is reason enough to avoid contact altogether. The late physicist Stephen Hawking was the most prominent voice expressing this concern. Hawking cautioned that we should avoid advertising our presence because any civilization advanced enough to detect and reach us would likely be so far beyond our technological level that the encounter could end badly for humanity. He drew parallels to historical encounters between technological superior and inferior human civilizations, noting that such encounters typically devastated the less advanced culture. Hawking's warnings resonated because they're grounded in human experience. European colonization of the Americas, Africa, Asia, and Oceania brought disease, exploitation, and genocide. Even when colonizers didn't intend harm, the disruption of traditional societies and introduction of foreign diseases killed millions. If aliens arrived with similar disregard for our well-being, we'd be helpless to resist. Our most advanced weapons would be primitive compared to theirs. We couldn't defend ourselves, negotiate from strength, or escape. But Hawking's analogy has limits. Interstellar travel is vastly more difficult than ocean voyages. A civilization capable of crossing light years of space represents a level of technological sophistication that might render Earth's resources irrelevant. They wouldn't need our water. Water is abundant in the universe, available on countless icy moons and comets. They wouldn't need our minerals. Asteroids contain the same elements without a native population to displace. They wouldn't need our biosphere. If they're interstellar, they presumably understand biology well enough to engineer their own ecosystems. What Earth offers that might be genuinely unique is life itself, particularly intelligent life. A civilization interested in studying diversity, understanding how life evolves under different conditions, or simply engaging with other minds, might find Earth valuable for those reasons. But destroying us or conquering us would defeat those purposes. You can't study a civilization you've annihilated. From this perspective, any civilization, advanced enough to reach us, would more likely be curious than hostile. Scientists rather than conquerors. Douglas V. Koch, president of the organization SETI International, which actively transmits messages to nearby stars, argues that Hawking's fears were based on flawed assumptions. Vakoch points out that any civilization capable of detecting Earth already knows we're here. Our atmosphere has contained oxygen for over 2 billion years, a clear biosignature visible to anyone with spectroscopic instruments. For the past century, we've been broadcasting radio signals into space. If predatory aliens wanted to find us, they've had ample time and evidence. Actively transmitting doesn't significantly increase our risk because we're already visible. Moreover, Vakoch argues, the very fact that we haven't been visited or destroyed suggests benign or indifferent aliens, not hostile ones. If the galaxy contained aggressive, expansionist civilizations with the technology to travel between stars, they'd likely have reached Earth already. Our solar system is about 4.5 billion years old, but the galaxy is over 13 billion years old. Plenty of time for an aggressive civilization to have arisen and spread. The fact that we're still here, unmolested, suggests either aliens are rare or they're not interested in conquering us, or interstellar travel is even more difficult than we think. The debate between Hawking's caution and Vakoch's optimism reflects deeper questions about the nature of intelligence and civilization. Do advanced civilizations inevitably become benign, transcending the violent competition that characterized their evolutionary origins? Or do the same competitive drives that powered their rise to dominance persist even at cosmic scales? We don't know. We have one example of intelligence, humanity, and we're still figuring out if we'll survive our own adolescence as a technological species. Planetary protection in the context of contact isn't just about biology and technology. It's about preserving our autonomy and agency as a species. If we received a message containing vast amounts of knowledge, how should we approach it? Should we immediately apply everything we learn, potentially transforming our civilization overnight? Or should we proceed slowly, integrating new knowledge carefully to avoid cultural disruption? there's a risk of becoming dependent on alien knowledge, losing our own capacity for innovation and problem solving. If aliens provide solutions to our challenges, we might stop developing our own solutions. Over time, we could become intellectually colonized, our science and culture shaped entirely by alien influences rather than our own creativity. This dependency could be as harmful as any biological contamination, eroding our identity and vitality as a civilization. Balancing the benefits of new knowledge against these risks would require wisdom and restraint, qualities not always abundant in human affairs. We'd need to think long term, considering not just immediate gains, but the kind of future we want to create. Do we want to be a civilization that solves its own problems, or one that relies on gifts from cosmic benefactors? The answer might determine our species' future trajectory more than any single technology or piece of information. Long-term implications, how contact changes everything. If we confirmed contact with an extraterrestrial civilization, the immediate reactions, dramatic and historic, would only be the beginning. The long-term implications would reshape every aspect of human civilization, from our scientific understanding to our philosophical frameworks, from our technological capabilities to our species' self-conception. Science would be transformed. The discovery would confirm that abiogenesis, the emergence of life from non-living chemistry, is not a unique miracle, but a replicable process that has occurred at least twice. This confirmation would energize research into the origins of life, providing a new data point that Earth-based studies can't offer. If we learned details about alien biochemistry, we'd gain insights into the range of possible chemical systems that can support life. This knowledge could revolutionize fields from biology to chemistry to materials science. If the aliens shared scientific knowledge, the impact could be even more profound, though we must emphasize this remains speculative. Imagine receiving a physics textbook from a civilization millions of years more advanced. If such sharing occurred, we might learn about phenomena we haven't discovered, principles that unify theories we currently view as separate, technologies that currently seem beyond reach. String theory, quantum gravity, unified field theories, all the puzzles that currently challenge our best physicists might find answers through insights from advanced aliens if they chose to share such information and if we could understand it. But integrating this knowledge wouldn't be straightforward. We'd need to verify it through our own experiments and observations. Just because aliens claim something is true doesn't make it so. They could be mistaken about certain aspects, or their understanding might be context dependent, valid for their situation, but not necessarily ours. Or, in a worst case scenario, they might be deliberately misinforming us. We'd need to approach alien scientific claims with the same skepticism we apply to terrestrial claims, testing everything rigorously before accepting it as valid. If their science checked out through rigorous testing, if experiments confirmed their claims, human science could advance by leaps rather than incremental steps. Technologies that might have taken centuries to develop could potentially arrive within decades, assuming we could understand and implement the information. Energy systems that tap into quantum phenomena we don't yet comprehend, propulsion systems based on principles we haven't discovered, computational architectures utilizing physics beyond our current understanding. All of these currently theoretical concepts might become engineering projects if the aliens provided such knowledge, and if we had the capability to make use of it. The technological revolution would have profound economic impacts, though predicting the specifics is essentially impossible. Industries based on technologies rendered obsolete would likely collapse. Fossil fuels, nuclear power, even renewable energy might become irrelevant if aliens provided blueprints for superior energy sources, a significant if that may never materialize. Transportation, communication, manufacturing, agriculture, every sector of the economy could potentially be transformed. The disruption would create winners and losers, potentially exacerbating inequality unless carefully managed through thoughtful policy. Governments would face the challenge of regulating technologies they don't fully understand, developed by civilizations with different ethics and priorities. A technology safe in one context might be dangerous in another. Regulations would need to balance innovation against safety, competition against stability, individual freedom against collective security. Getting this balance right would be critical to avoiding catastrophe. Medicine could potentially advance dramatically, assuming aliens chose to share relevant biological knowledge, and assuming that knowledge could be applied to human biology. If aliens shared insights about biology and health mechanisms that work across different life forms, we might gain understanding that helps with preventing or curing diseases, extending lifespan, or enhancing cognitive or physical capabilities. We might learn approaches to repairing genetic damage, regenerating tissues, or addressing aging, though all of this remains highly speculative. These theoretical possibilities raise profound ethical questions that we would need to grapple with. Who gets access to such treatments if they become available? If life extension becomes possible, does everyone have a right to it? Or is it a privilege for the wealthy? How do we handle population growth if people stop dying at current rates? What does it mean to be human if we gain the ability to modify ourselves fundamentally? These questions would need serious consideration before implementing any transformative medical technologies. Philosophically, contact would force humanity to reconsider fundamental assumptions. The question, "Are we alone?" would be answered. We'd know definitively that intelligence is not unique to Earth. This knowledge would complete a process that began with the Copernican revolution. First, we learned Earth isn't the center of the universe. Then, that our sun is an ordinary star among billions. Then, that our galaxy is one among trillions. Now we'd learn that even our existence as intelligent beings isn't unique. We'd become one civilization. Among at least two confirmed examples, our history and struggles. One thread in what appears to be a larger cosmic story. For some, this realization could be liberating. It might place human conflicts and anxieties in perspective. Wars, political struggles, cultural differences. All the divisions that seem so important might appear less significant when viewed against the backdrop of a universe known to contain other intelligences. We might find unity in our shared humanity, recognizing that our commonalities far outweigh our differences. For others, the realization might be deeply unsettling. If we're not special in a cosmic sense, if our existence is just one instance among potentially many, what meaning does life have? Religions and philosophies that place humanity at the center of cosmic drama would face significant challenges. Some belief systems would likely adapt, reinterpreting their narratives to accommodate aliens. Others might resist, insisting on human uniqueness despite evidence of other intelligences. Existential philosophy would grapple with these questions. Is meaning inherent in the universe, or do we create it? If aliens have different values and purposes, does that validate moral relativism, or are there universal ethics? Can beings with radically different experiences and cognition share understanding, or is each intelligence fundamentally isolated by its unique perspective? Politically, contact might shift global power dynamics. If one nation or bloc gained preferential access to alien knowledge, they could achieve decisive strategic advantages. This asymmetry could lead to conflict, or conversely, to new forms of cooperation, as nations recognize that ensuring broad access is in everyone's interest. International institutions might be strengthened, given new mandates to coordinate humanity's interaction with aliens and manage the integration of alien knowledge. Or contact might fragment humanity. Different nations and cultures might interpret the aliens' message differently, leading to competing narratives and agendas. Religions might split into factions, some embracing the aliens as part of divine plan, others rejecting them as deception. Conspiracy theories would proliferate, with some groups claiming the aliens are allied with particular governments or factions. The potential for division and conflict is real. Culturally, contact would inspire a renaissance. Artists, writers, musicians, filmmakers, all would respond to this cosmic moment, exploring its implications through their media. We'd see an explosion of creativity as people tried to make sense of the new reality. Literature would imagine encounters, dialogues, futures shaped by alien contact. Visual arts would depict aliens and their civilizations, blending speculation with whatever information we'd received. Music would capture the wonder, fear, hope, and confusion that contact engenders. Education would be transformed. Curricula would need to include information about the aliens, their civilization, and the implications of their existence. Students would study exobiology, interstellar communication, comparative civilization, subjects that currently don't exist as formal disciplines. The discovery would make science and space exploration more relevant and exciting to many students, potentially inspiring a generation of researchers, engineers, and explorers. But there's also a risk of becoming obsessed with the aliens to the exclusion of terrestrial concerns. If we focus all our attention and resources on understanding and communicating with them, we might neglect problems here on Earth: poverty, disease, environmental degradation, social injustice. The aliens wouldn't solve these problems for us. They'd remain our responsibility, requiring our attention and effort. Contact could distract us from our obligations to each other and to our planet. The question of whether to respond to the aliens' message would remain contentious. If we did decide to reply, composing the message would be an enormous challenge. What do we say? How do we represent humanity's diversity? Do we emphasize our achievements or our struggles? Do we present ourselves as peaceful or acknowledge our violent history? Do we ask for help with our problems or try to appear self-sufficient? The message's content would shape the aliens' understanding of us, potentially influencing how they interact with us. A truthful message might reveal our vulnerabilities, but a deceptive one could backfire if they see through it. The stakes are high, and there are no precedents to guide us. Assuming we eventually sent a response, the wait for a reply would be measured in decades or centuries, depending on the alien's distance. This lag creates an interesting dynamic. Generations would pass between exchanges. The civilization that receives our response might be significantly different from the one that sent the original message. Similarly, we would change during the wait. The humans who eventually receive the alien's next message might view our initial response as quaint or embarrassing. This temporal dimension fundamentally alters the nature of interstellar communication. It's not a dialogue, but a series of monologues separated by vast gulfs of time. Each message is a time capsule, a snapshot of a civilization at a particular moment. Over many exchanges, we'd assemble a history of each other's development, watching civilizations evolve across cosmic timescales. In the very long term, assuming contact is benign and ongoing, humanity might join a broader community of civilizations. We might gain access to a galactic network, a cosmic internet connecting thousands or millions of species. The knowledge available would be staggering. The diversity of perspectives, mind expanding. We'd learn not just about science and technology, but about art, philosophy, ethics, spirituality, all the ways different minds make sense of on existence. This participation would require humility and openness. We'd be the newcomers, the latest arrivals to an ancient community. We'd have much to learn, and, initially at least, little to teach. Our technological and scientific knowledge would be primitive compared to civilizations millions of years old, but we might offer fresh perspectives, new ideas that come from our unique history and evolutionary path. Every civilization's experience is different, and even a young civilization can contribute. The ultimate question is whether contact would make humanity better or worse, wiser or more foolish, unified or divided. The answer probably depends less on the aliens than on us. How we respond, how we integrate new knowledge, how we navigate the challenges and opportunities, these choices would determine the outcome. Contact doesn't guarantee a utopian future, nor does it doom us to catastrophe. It simply presents us with possibilities, and what we make of those possibilities is up to us. The dark forest theory and potential dangers. Not everyone believes that contact with aliens would be beneficial or even safe. A significant minority of scientists and thinkers warn that actively seeking contact could be humanity's greatest mistake. This perspective is perhaps best articulated in what's known as the dark forest hypothesis, a thought experiment popularized by Chinese science fiction author Liu Cixin in his novel The Dark Forest, the second book in the Three-Body Problem trilogy. While originating in fiction, the concept has sparked serious scientific discussion about the potential risks of contact. The dark forest hypothesis, as a theoretical framework, begins with two axioms. First, survival is the primary need of any civilization. Second, the total amount of matter and energy in the universe is finite, and expanding civilizations will eventually compete for resources. Given these axioms, the hypothesis argues that the universe is like a dark forest. Every civilization is a hunter moving quietly through the trees, trying to remain hidden while searching for other hunters. When a hunter detects another hunter in the dark forest, what happens? The safest strategy, according to the hypothesis, is to attack immediately and overwhelmingly. Why? Because the other hunter might attack first if given the chance. Even if the other hunter appears peaceful, they might be deceptive, luring you into complacency before striking. And even if they're genuinely peaceful now, they might not remain so. Their civilization might change, becoming aggressive, or they might share your location with others who are aggressive. The only way to guarantee your own survival is to eliminate potential threats before they become actual threats. This logic leads to a grim conclusion. The galaxy should be full of civilizations hiding in silence, each afraid to reveal itself, each ready to destroy anyone who does. The Great Silence, the apparent absence of detectable alien civilizations despite the vast number of stars, isn't because aliens don't exist. It's because those who announced their presence were destroyed, and the survivors learned to stay quiet. The dark forest hypothesis is chilling, but not necessarily accurate. It rests on several assumptions that might be wrong. First, it assumes civilizations inevitably expand and compete for resources, but resources might be abundant enough that competition isn't necessary, especially if civilizations develop technologies like matter energy conversion or harness stellar energy efficiently. Advanced civilizations might have access to effectively limitless resources, making conflict unnecessary. Second, the hypothesis assumes civilizations prioritize physical survival above all else. But as civilizations mature, their values might shift. They might prioritize knowledge, experience, art, compassion, virtues that don't require physical expansion or conflict. A civilization that has transcended scarcity might not care about controlling more territory or resources. Third, the hypothesis assumes no way to verify another civilization's intentions without destroying them. But communication, even across vast distances, might allow civilizations to develop trust over time. Consistent peaceful behavior over millennia could establish credibility. Game theory suggests that cooperation can emerge even between selfish actors if they expect repeated interactions. Fourth, the hypothesis ignores the possibility of defensive technologies that make aggression pointless. If sufficiently advanced civilizations can shield themselves from attack or retaliate decisively, the incentive for preemptive strikes disappears. Mutual assured destruction, the logic that prevented nuclear war during the Cold War, might apply on a galactic scale. That said, the dark forest hypothesis highlights real risks. We don't know alien motivations or capabilities. Announcing our presence might attract unwanted attention. This concern was central to Stephen Hawking's warnings about contact. Hawking argued that history provides countless examples of encounters between civilizations at different technological levels, ending badly for the less advanced. European colonization of the Americas, Africa, and Oceania brought disease, slavery, and genocide. Indigenous populations were often decimated or destroyed. Hawking acknowledged that we can't know alien motivations, but he argued that we should err on the side of caution. If there's even a small chance that contact could be catastrophic, we should avoid taking that risk. The stakes are too high. We could be betting the survival of our species on the hope that aliens are benign. This seems reckless when the alternative, remaining quiet, costs us nothing. Critics of Hawking's position, including Douglas Vakoch, argue that it's already too late to hide. Earth has been broadcasting its presence for decades through radio and television. Signals. Any civilization within 100 light years with sufficiently sensitive instruments could have detected us. Moreover, Earth's biosignatures have been visible for billions of years. Oxygen in our atmosphere, methane, and other organic gases, these are detectable across interstellar distances. We can't hide anymore if we ever could. Furthermore, critics argue the probability of contact with hostile aliens is extremely low, perhaps lower than many terrestrial risks we accept without hesitation. The distances between stars are vast. Interstellar travel is difficult and expensive, even for advanced civilizations. Why would aliens expend the resources to travel light years just to harm us when there are far easier ways to obtain whatever resources they need? If aliens wanted water, they could mine comets or icy moons, which are abundant throughout the galaxy and don't have native populations to resist. If they wanted minerals, asteroids contain the same elements as Earth without the complications of a living biosphere and an intelligent species. If they wanted energy, they could harness their own star using technologies like Dyson spheres. The only thing Earth offers that might be genuinely rare is life itself, particularly intelligent life. And if that's what interests them, destroying us would defeat the purpose. This logic suggests that aliens capable of reaching Earth would more likely be scientists or explorers than conquerors. They'd want to study us, communicate with us, learn from us. This doesn't guarantee they'd be friendly, but it does suggest their interests might align with our survival. After all, you can't study a civilization you've annihilated. Another argument against the dark forest hypothesis is the Fermi paradox itself. If aggressive, expansionist civilizations exist and follow the dark forest logic, they should have spread throughout the galaxy long ago, eliminating all potential competitors. The fact that we're still here has led researchers to propose several alternative explanations, though all remain speculative. The zoo hypothesis, first proposed by radio astronomer John Ball in 1973, offers one such alternative. According to this idea, perhaps advanced civilizations know about us, but deliberately avoid contact, observing us as we might observe animals in a nature preserve. Based on this framework, they might have ethical principles against interfering with less advanced civilizations, letting us develop naturally without outside influence. Or they might find us too primitive to be interesting, waiting until we reach a certain level of development before making contact. However, this hypothesis is purely speculative and has no observational evidence to support it. The transcension hypothesis, proposed by futurist John Smart, suggests another possibility, that sufficiently advanced civilizations move beyond physical existence, transcending into higher dimensions, virtual realities, or states of being we can't comprehend. If this pattern holds across civilizations, the galaxy might be filled with advanced intelligences, but they're no longer operating in the physical universe we observe. They wouldn't be detectable through radio searches or visible as Dyson spheres. They'd have left the material world behind, pursuing goals incomprehensible to us. This remains an intriguing idea, but one without any empirical support. All of these hypotheses are speculative. We don't have enough data to determine which, if any, is correct. The universe might operate according to dark forest principles, or resemble a zoo with passive observers, or be filled with transcended civilizations we simply can't detect. We simply don't know. And because we don't know, we must make choices under uncertainty. This uncertainty creates a genuine dilemma. If we broadcast aggressively, announcing our presence loudly and repeatedly, we might attract hostile attention, assuming hostile civilizations exist and are listening. But if we remain silent, We might miss the opportunity to join a community of civilizations, to learn from them, to contribute to a galactic conversation. There's no risk-free option, and reasonable scientists disagree about which approach makes more sense. One compromise is passive SETI combined with careful limited active SETI. We listen broadly, scanning the skies for signals, while occasionally broadcasting carefully crafted messages to selected targets. This approach balances curiosity with caution. We're not shouting indiscriminately into the void, but we're not hiding either. We're acknowledging the risks while pursuing the benefits. Another consideration is that our concerns might be anthropocentric. We're projecting human psychology and history onto aliens who might think completely differently. Humans have often been competitive, territorial, and violent because those traits were adaptive during our evolutionary history. But aliens might have evolved under different conditions that favored cooperation, empathy, or other traits. Their psychology might be incomprehensible to us, neither friendly nor hostile in ways we'd recognize. Ultimately, the debate over active SETI versus passive SETI reflects deeper questions about risk tolerance, human nature, and our place in the cosmos. Are we fundamentally vulnerable, surrounded by potential threats, needing to hide to survive? Or are we part of a universe where intelligent life, though rare, tends toward benevolence or at least neutrality? The answer shapes not just our SETI strategy, but our self-image as a species and our hopes for the future. What we would try to communicate. If humanity decided to send a message to an alien civilization, either in response to a received signal or as an initial attempt to make contact, what would we say? This question has occupied scientists, linguists, artists, and philosophers for decades. The challenge is enormous. How do you communicate with beings whose language, sensory modalities, and conceptual frameworks might be completely alien? The history of human attempts provides instructive examples. The Pioneer plaques, attached to Pioneer 10 and 11 spacecraft, launched in 1972 and 1973, represented early efforts. The plaques, designed by Carl Sagan and Frank Drake, contained simple line drawings etched into gold anodized aluminum. The images showed a nude man and woman standing next to a representation of the spacecraft for scale, the transition of a hydrogen atom from one energy state to another to establish a unit of time and distance, a map of our solar system showing Earth's position, and a radial pattern indicating Earth's location relative to 14 pulsars and the galactic center. The plaques assumed aliens would recognize certain universal concepts. Hydrogen is the most abundant element in the universe. Its properties should be universally known to any technological civilization. Pulsars are natural cosmic beacons with distinctive periods. They could serve as landmarks for navigation and dating. The images attempted to convey information visually, assuming aliens would understand the concept of pictorial representation. Critics pointed out several assumptions that might not hold. Would aliens understand that the images are meant to depict physical objects rather than being abstract symbols? Would they recognize humans as bipedal beings or interpret the drawings differently? Would they understand the scale reference? Or might they think the spacecraft is enormous and the humans tiny, or vice versa? These ambiguities illustrate the difficulty of cross-species communication. The Voyager Golden Records, launched in 1977, represented a far more ambitious attempt. Instead of simple diagrams, The records contained 116 images, greetings in 55 languages, natural sounds like thunder and birdsong, music from diverse cultures, and even encoded brainwaves from a human meditator. The records also included scientific information, mathematical definitions, physical constants, diagrams of DNA, the solar system, and human anatomy. The Voyager team tried to provide context that would make the information interpretable. The record's cover included diagrams showing how to play the record, establishing the rotational speed and stylus placement. A pulsar map indicated Earth's location. Binary numbers defined units of time and distance. The idea was to build up from simple universal concepts to more complex, culture-specific information. The music selection on the Voyager records has been both praised and criticized. It included Bach, Beethoven, Mozart, traditional music from Peru, Senegal, Java, India, and many other cultures, as well as blues, jazz, and rock and roll. The goal was to represent human cultural diversity and artistic achievement, but critics noted that Western classical music was overrepresented, and the selection reflected the tastes and biases of the small committee that made the choices. Could any selection truly represent all of humanity? The Arecibo message, transmitted in 1974, took a different approach. Instead of sending physical artifacts, it broadcast a radio signal encoded with binary information. The message consisted of 1,679 bits, a number chosen because it's the product of two primes, 73 and 23. This suggests arranging the bits as a 73 by 23 grid, creating a pictogram. The image shows the numbers 1 through 10 in binary, the atomic numbers of elements essential for life, the structure of DNA, a human figure, Earth's population, the solar system, and the Arecibo telescope. The Arecibo message is elegant and information-dense, but it assumes aliens would recognize the prime number structure and understand binary representation. It also assumes they'd interpret the pictogram correctly, which isn't guaranteed. Without instructions, the message could be misunderstood or ignored. More recent proposals have become even more sophisticated. The Beacon in the Galaxy message, developed by an international team led by Jonathan Jiang at NASA's Jet Propulsion Laboratory, combines elements from previous messages with new information about Earth's current state. It includes updated images, data about human civilization's technological level, information about our genetic and biochemical basis, and a map showing Earth's location with unprecedented precision, using globular clusters as reference points. All these messages share a common strategy. Start with simple universal concepts and build toward more complex information. Mathematics and physics provide the foundation because they're presumably universal. The laws of nature operate the same way everywhere, giving us common ground with any technological civilization. Once we've established basic concepts like numbers, units, and physical constants, we can layer on more specific information about our biology, our planet, our civilization. But this approach has limitations. It assumes aliens think analytically and scientifically like human scientists. What if they don't? What if their primary mode of understanding is aesthetic, emotional, or spiritual rather than analytical? What if they perceive reality in ways so different from ours that our mathematical and physical descriptions make no sense to them? Some researchers have proposed alternative approaches. Instead of sending scientific information, we could send art, music, poetry, things that convey emotional and aesthetic content without relying on logical analysis. An alien civilization might not understand our physics, but they might resonate with the emotional content of a Beethoven symphony or a haiku. This approach risks being even more ambiguous, but might communicate something essential about what it means to be human in ways that raw data cannot. Linguistic approaches have also been explored, though their effectiveness remains uncertain. Could we teach aliens a human language by sending examples of speech paired with images or actions? This is how children learn language, through association and context. We could send a message that shows an image of water while speaking the word water, then repeat with other objects and concepts. Over time, aliens might learn enough vocabulary to understand more complex messages, or they might find the entire approach incomprehensible. The problem is that human languages encode assumptions about how we perceive and categorize the world. Our grammar reflects temporal concepts like past, present, and future, spatial concepts like near and far, social concepts like speaker, listener, and third party. If aliens perceive time or space differently, if their sensory experience of reality is fundamentally unlike ours, our grammatical structures might make no sense to them. This doesn't mean the approach is impossible, but it does suggest significant challenges. Mathematicians have proposed constructing artificial languages based purely on logic and mathematics. These languages would avoid the cultural and perceptual assumptions built into natural languages. Messages in such languages could be unambiguous and verifiable. The challenge is that they'd be limited to expressing logical and mathematical ideas, not emotional, aesthetic, or cultural content. Another question is what content to include. Should we present humanity's best achievements, our art, our science, our ethical ideals? Or should we be honest about our flaws, our violence, our environmental destruction? A sanitized message might misrepresent who we are, while a brutally honest one might alarm aliens or suggest we're too dangerous to engage with. Some argue we should emphasize our diversity, showing that humanity isn't monolithic. Messages should include contributions from different cultures, languages, and perspectives, representing Earth's cultural richness. Others worry that too much diversity might confuse aliens, making it harder to extract a coherent understanding of humanity. The ethical question of who decides what to send remains contentious. No single person or nation can legitimately speak for all of humanity. Any message should ideally be developed through international consultation, incorporating input from scientists, artists, ethicists, and representatives of diverse cultures. But achieving such consensus is difficult, time-consuming, and potentially impossible given the diversity of human values and interests. In practice, messages have been composed by small groups of scientists and enthusiasts, often without broad consultation. This raises questions about legitimacy and representation. Do these groups have the right to speak for humanity? What if their messages misrepresent us or include information that puts us at risk? There's also the question of whether to include our location. The Arecibo message and Voyager records included information about Earth's position in the galaxy. This makes sense if we want aliens to find us, but it's risky if there's any chance they might be hostile. Some argue we should send messages without revealing our exact location, providing general information about our existence without making it easy to track us down. But hiding our location might be pointless. If aliens have detected our radio signals or spectroscopic signatures, they already know where we are. And if we're responding to a message from them, they presumably know our location because they know where their message was received. The secrecy might provide a false sense of security without actual benefit. Ultimately, any message we send will be imperfect, a product of our limited understanding and biases. We can't know in advance what aliens will make of it. We can only do our best to communicate clearly and honestly, acknowledging the enormous uncertainties involved. The message becomes less about conveying specific information and more about announcing our existence, our curiosity, our desire to connect across the cosmic void. It's a gesture, a reaching out, an assertion that we're here and we want to be known. Lessons from false alarms and near misses. The history of SETI is punctuated by moments of excitement, followed by disappointment, signals that seemed promising initially, but turned out to be natural phenomena or human interference. These false alarms provide valuable lessons about the verification process, the importance of skepticism, and the challenges of distinguishing artificial signals from natural ones. The WOW signal remains the most famous near miss. Detected on August 15, 1977, by Ohio State University's Big Ear Radio Telescope, it appeared to have all the characteristics of an artificial transmission. Narrowband, strong, coming from a specific direction in space, and lasting exactly the time expected for a cosmic source moving through the telescope's beam as Earth rotated. Astronomer Jerry Amon, reviewing the data, was so struck by the signal's characteristics that he wrote "wow" on the printout. The signal was never convincingly detected again, despite numerous follow-up observations. For decades, it remained unexplained. Was it aliens? An unknown natural phenomenon? Interference from an Earth satellite or aircraft? Recent analysis in 2024 and 2025 by the Arecibo WOW project has refined our understanding. By digitizing archival data using modern techniques, researchers found the signal was even more powerful than originally estimated, approximately 250 Janskis. They also identified similar but weaker signals in the data, suggesting a possible natural explanation involving transient phenomena in cold hydrogen clouds. Even if the WOW signal wasn't aliens, it taught us valuable lessons. It demonstrated that verification requires replication. One detection, no matter how compelling, isn't enough. We need to see the signal multiple times, ideally from multiple locations, before claiming discovery. The WOW signal also highlighted the importance of archiving data. Decades later, researchers could re-examine the original observations using tools that didn't exist in 1977, extracting new insights. In 2015, astronomers noticed unusual dimming patterns in a star, called KIC 8462852, nicknamed Tabby's star, after astronomer Tabitha Boyajian, who led the research. The star's brightness dropped irregularly, sometimes by over 20%. Far more than would be expected from an orbiting planet. The dimming pattern didn't fit any known natural explanation. One possibility, though speculative, was that the dimming was caused by alien megastructures orbiting the star, perhaps a Dyson swarm of satellites harvesting the star's energy. Media coverage seized on the alien hypothesis, generating enormous public interest. But astronomers emphasized caution. Extraordinary claims require extraordinary evidence, and the alien explanation, while exciting, was far less likely than unknown natural phenomena. Further, observations revealed that the star's dimming was wavelength dependent, with more dimming in blue light than red. This pattern suggested dust, not solid structures, was causing the dimming, A cloud of dust orbiting the star, perhaps from a shattered comet or protoplanetary disk, could explain the observations without invoking aliens. The Tabby's star episode illustrated the danger of premature speculation. While it's important to consider all possibilities, including artificial ones, we should be careful not to jump to conclusions. The most exotic explanation is rarely the correct one. Nature is full of phenomena we don't yet understand. Before claiming aliens, we need to rule out all plausible natural explanations, a process that can take years of careful observation and analysis. In 2017, astronomers detected an interstellar object passing through our solar system, later named Oumuamua, Hawaiian for scout, or messenger from afar arriving first. The object's trajectory indicated it came from interstellar space, making it the first confirmed interstellar visitor. Its shape was unusual, estimated to be highly elongated, perhaps 10 times longer than it was wide. Its motion was also strange, accelerating slightly as it left the solar system in a way that couldn't be fully explained by the sun's gravity alone. Harvard astronomer Avi Loeb suggested provocatively that Oumuamua might be an alien light sail, a thin reflective sheet propelled by stellar radiation pressure. This would explain both the unusual shape and the non-gravitational acceleration. Most astronomers disagreed, arguing that outgassing, the release of volatile materials as the object warmed, could explain the acceleration. Even though no coma or tail was visible, outgassing might have occurred asymmetrically in ways that didn't produce observable emissions. The debate over Oumuamua continues. It's probably a natural object, but its unusual properties make it intriguing. The encounter highlighted the need for better observation capabilities. By the time astronomers realized Oumuamua was interstellar, it was already leaving the solar system. We only had a brief window to study it. Future interstellar objects, and there are likely many passing through unnoticed, should be detected earlier and studied more thoroughly. Pulsars, discovered in 1967 by graduate student Jocelyn Bell Burnell and her supervisor Anthony Hewish at Cambridge University, were initially so baffling that the research team nicknamed the first one LGM-1 for Little Green Men. The pulses were extraordinarily regular, repeating with precision that rivaled atomic clocks. No known natural process could produce such regular signals. The possibility that they were artificial beacons from alien civilizations was seriously considered by the team. However, the discovery of more pulsars over the following months, each with different periods, made the alien hypothesis increasingly unlikely. Why would aliens build so many beacons, each transmitting at different rates with no apparent pattern? As observations accumulated, astronomers developed a natural explanation. Pulsars are rapidly rotating neutron stars with intense magnetic fields. As the star rotates, beams of radiation sweep across space like lighthouse beams. When a beam points toward Earth, we detect a pulse. The regularity comes from the star's rotation, stabilized by its enormous density and angular momentum. The pulsar story demonstrates the importance of multiple detections. If only one pulsar had been found, and never another, the mystery might have persisted. But finding many, each with unique properties, allowed astronomers to identify patterns and develop theories. Anomalies that resist explanation might be aliens, but they're more likely to be new natural phenomena we haven't encountered before. Fast radio bursts, or FRBs, are another recent mystery. These are millisecond-long pulses of radio emission, incredibly powerful but brief. The first FRB was discovered in 2007 by astronomer Duncan Lorimer and his team, while analyzing archival data from 2001 collected by the Parkes Telescope in Australia. It's sometimes called the Lorimer Burst in his honor. Since then, hundreds have been detected. Most are one-time events, never repeating from the same location. A few repeat irregularly. Their origins are still debated, with leading theories involving magnetars, highly magnetized neutron stars, colliding neutron stars, or other exotic phenomena in extreme environments. Some speculation suggested FRB might be artificial, perhaps from alien spacecraft propulsion systems or directed energy weapons. The short duration and immense power are consistent with advanced technology, but as more FRBs were detected and studied, natural explanations became more compelling. The distribution of FRBs across the sky is uniform, suggesting they originate from cosmological distances throughout the universe. If they were artificial, we'd expect them to cluster around galaxies with suitable conditions for intelligent life. The lack of such clustering supports natural origins. Each of these cases reinforces the same lessons. First, verification requires patience and rigor. Initial detections, no matter how exciting, must be replicated and analyzed carefully. Second, natural explanations should be exhaustively explored before invoking artificial ones. The universe is full of phenomena we don't understand. Third, technology improves over time, allowing reanalysis of old data with new tools. What seemed inexplicable decades ago might become clear with better instruments and understanding. The false alarms also remind us of the importance of managing expectations. Media coverage often sensationalizes discoveries, emphasizing the most exotic interpretations while downplaying uncertainties. Scientists have a responsibility to communicate clearly about what's known and what's speculation, helping the public understand the process of scientific inquiry. Discoveries unfold gradually through painstaking observation and analysis, not through sudden eureka moments. When the real signal arrives, if it ever does, we'll need to apply these lessons. The initial detection will generate excitement, but we must resist the urge to announce prematurely. Verification will take time, perhaps months or years. We'll need to rule out interference, natural phenomena, and equipment errors. Only when we're confident will announcement be appropriate, and even then we should acknowledge uncertainties, clearly distinguishing what we know from what we speculate. These false alarms haven't discouraged the search. If anything, they've refined it, teaching us what to look for and how to verify. Each near miss brings us closer to developing the protocols and expertise needed to recognize the real thing when it happens. And they remind us that the universe is stranger and more diverse than we imagine, filled with phenomena that challenge our understanding and expand our knowledge. Conclusion: living in the age of possibility, we stand at a unique moment in human history. For the first time, we have the technological capability to detect signals from other civilizations, if they exist and are transmitting. We can send our own messages across the interstellar void. We're discovering thousands of exoplanets, many in the habitable zones of their stars. We're developing instruments capable of analyzing those planets' atmospheres for biosignatures or technosignatures. Contact, if it's going to happen, might happen in our lifetimes or our children's lifetimes. We've explored the protocols that guide our response to detection, the scientific process of verification and analysis, the societal and political impacts that would ripple across human civilization. We've examined the biological and security concerns, the long-term implications for science, technology, philosophy, and culture. We've confronted the dark possibility that contact might be dangerous, a risk we take by announcing our presence. We've considered what we might try to communicate and what we might learn from messages we receive. And we've learned from false alarms and near misses, sharpening our ability to distinguish artificial signals from natural phenomena. The question, what happens if we're contacted by aliens, doesn't have a single answer. The outcome depends on countless variables: the nature of the contact, the intentions of the aliens, the state of human civilization at the time, the decisions we make in response. But understanding the possibilities helps us prepare. We're not completely in the dark. We have frameworks, protocols, expertise. We've thought about this scenario, gaming out the challenges and opportunities. More importantly, the question forces us to confront deeper issues about who we are and what we value. Are we a species mature enough to handle contact with an advanced civilization? Can we cooperate internationally, setting aside narrow interests for the common good? Can we communicate honestly and openly with beings whose nature we can't fully comprehend? Can we learn and grow from the encounter without losing our own identity and agency? These questions matter even if contact never happens. Preparing for contact with aliens makes us think about how we relate to each other, how we manage powerful technologies, how we balance curiosity against caution. It pushes us to imagine futures beyond our current concerns, to think on timescales longer than election cycles or quarterly earnings reports. It reminds us that we're part of something larger than ourselves, citizens of a universe that may contain countless other civilizations, each with their own stories and struggles. The search for extraterrestrial intelligence is fundamentally an expression of hope. We search because we believe the universe might contain others like us, minds seeking connection across the void. We search because we want to know if we're alone or if we're part of a cosmic community. We search because the question matters, and because not searching would mean accepting ignorance about one of the deepest questions we can ask. Whether or not we find aliens, the search itself is valuable. It advances science, developing new technologies and methodologies that have applications far beyond SETI. It inspires people, showing that humanity is capable of thinking beyond immediate concerns and pursuing grand visions. It unites us, creating a project that transcends national boundaries and cultural differences, and it enriches our understanding of ourselves by forcing us to imagine others. If contact does occur, it will be the most significant event in human history. The discovery of other intelligences would reshape every aspect of our civilization, from our scientific understanding to our philosophical frameworks, from our technology to our self-conception. We'd no longer be able to think of ourselves as unique or central. We'd be one civilization among many, our existence part of a larger pattern. This realization could be humbling or liberating, depending on our response. We might feel diminished, our achievements made trivial by comparison to more advanced civilizations, or we might feel connected, part of a universe rich with diversity and possibility. We might fear what contact reveals about our vulnerability, or we might embrace the opportunity to learn and grow beyond our current limitations. The choice of how we respond would define us as a species. Would we meet the challenge with wisdom and courage, or with fear and narrow self-interest? Would we see contact as an opportunity for growth or a threat to our security? Would we rise to the occasion, demonstrating the best of what humanity can be? Or would we fracture our divisions and conflicts, preventing a coherent response? These are questions we can't answer in advance. We can only prepare as best we can, building institutions and protocols, fostering international cooperation, educating the public, and thinking deeply about the implications. And then, if the moment comes, we can hope that we're ready, that we've laid enough groundwork to navigate the challenges and seize the opportunities. In the meantime, we continue the search. Radio telescopes scan the skies. Optical observatories watch for laser flashes. Surveys catalog exoplanets, searching for signs of life. Researchers analyze data, looking for patterns that might indicate intelligence. The work is painstaking and often thankless, with years of null results. But the searchers persist, motivated by curiosity and the slim but real possibility of success. And every night, when you look up at the stars, you can wonder, is anyone out there looking back? Is there, somewhere among those countless points of light, a civilization asking the same questions we ask? Are they searching for us as we search for them? Have they already found us, observing from afar, waiting for us to reach a certain level before making contact? Or are we truly alone, the only minds in a vast, empty universe? We don't know the answers yet, but we're looking, we're listening, we're reaching out. And that, perhaps, is what makes us human: the ability to ask questions we can't yet answer, to seek knowledge beyond our grasp, to hope for connection even across cosmic distances. Contact with aliens would change everything, but the search itself, the act of looking and wondering, has already changed us. It's made us think bigger, dream wider, and recognize our place in a universe far stranger and more magnificent than we ever imagined. If you found this exploration meaningful, please consider liking and subscribing to help the channel grow. Thank you for joining me on this journey through one of humanity's most profound questions. Keep looking up, keep wondering, and keep searching for answers among the stars. Good night.